Welcome. Today we're going to talk about a multilayer perceptron. As the name suggests, this is going to be a broad generalization of the perceptron. So it's going to be, you'll see the resemblance to the perceptron, but you'll also see that it can be much more powerful. So let's start off by looking at something we already looked at before, which is the XOR problem. And that is, we're just going to try to train a classifier to represent the XOR function. So let me draw this for you. Going to look something like this. Let's start by drawing some axes. Then here is 0, 0, 1, 1. And let's put some points here. And yeah, just recall that this is the XOR function, or maybe the inverse of the XOR, depending on what you consider to be plus or minus. And yeah, so the sort of claim which I showed you by picture before is that no perceptron is able to correctly classify all 4 of these points. And you can kind of see this by picture. If you try to draw a line, you can't really draw any line which gets the same. You can't find any line which really splits these so that the pluses appear on one side and the minuses appear on the other side. So that's like a proof by picture roughly, but let me actually prove it for you more mathematically, that there is no perceptron which is able to get all 4 points correctly classified. And so let's do it like follows. Let's suppose our model has y hat equal to the inner product of w comma x plus b. Pretty standard perceptron, and recall our classification will be a point is +1 if y hat is greater than 0, and it'll be -1 if it's less than 0. So let's look at the points we have here. So we have 4 points. So the first one is going to be 0, 0, and the label here is -1. So now what does this imply about our perceptron, about our parameters here? Well, we know that y hat for this should be less than 0. Well, what is this? If we take the inner product of w and x1, then we'll just get 0 because it's 0. And so plus b will be, it just basically tells us that b has to be less than 0, because essentially this term will just cancel out here, and therefore we need this to be the same sign as what we wanted, which is -1. Okay, so that's one constraint that we have. If we want to classify this point correctly, this point right here correctly, we need b to be less than 0. Let's go on to the next point. And this sort of thing would imply that, what would we need? Well, we take the inner product of w and x, and that gives us that w2 plus the b. This is going to be the prediction y hat, and we want that y hat is greater than 0, because that'll make it so that the prediction is going to be 1. Similarly, we can do x3. And that implies very similar things by exactly the same logic. And the fourth one is not too different. This one says that if you take w1 plus w2 plus b, that'll be the inner product of right here. This will say that we need this to be less than 0. If not, then this would be misclassified. So okay, we've got these 4 constraints, and let's just take a look at what happens if we put them together in the right way. So if we take this one and this one, then putting those together, those imply that w1 plus w2 plus 2b is less than 0. And on the other hand, if we take the other 2 and put those together, those seem to imply that we get w1 plus w2 plus 2b is less than 0. Sorry, not less than 0, greater than 0. So you can see how these two are contradictory. In particular, we need simultaneously for this term on this expression on the left to be less than 0 as well as greater than 0 in order for all 4 of these points to be classified correctly, which is a contradiction. That's the end of the proof, and this proof essentially shows that you can't simultaneously classify all 4 points correctly in the XOR function with a perceptron. So yeah, this is a more rigorous proof of the sort of proof by picture, which I showed you just by drawing lines here. Okay, so this shows us that we can't use the perceptrons here, and what can we do as a result of this? Well, there's a few things we can do. So how to learn XOR. And you might be one thing to wonder is why do we even care about XOR? What's so special about it? Well, the main thing that's important about it is the fact that this is a very, very simple function. It seems like so simple, so basic. Any human can tell you how to classify this, and it doesn't seem so complex. But it seems like our models aren't good enough. And we've gotten around this before, the fact that linear models can't learn XOR. And the way we did that before was using kernels. And just to recall what we did here was we would first apply a mapping to data. And then what we would do is use a linear classifier on top of it, or a linear model on top. In other words, the important thing here is the first part, in which we had a fancier representation of our data. So yeah, representations are kind of what really matter. If you manage to find the right representation of your data, then you can use a linear model or a very simple model on top of it, and it'll be super, super easy. So the generic way to do this is like using kernels. That is, there's a toolbox of common kernels that we have, which you can just apply to your data, and this will give you something nice. Then a lot of machine learning for many years was focused on what are known as handcrafted features. By this, I mean, suppose you're working on a specific application area, you kind of know things about your data and what sort of mappings and what sort of things you need to extract out of your data. So you suppose you're given some vector X, and maybe you know that taking the squares of each thing or combining them in some fancy way is kind of the right thing to do. You can see this maybe as a type of kernel, but kernels are often referred to sort of just generic ones, whereas handcrafted features are more often things that you discover through being an expert in this area and realizing that, okay, if we make this representation of our data, that is, we sort of add in new dimensions to our feature vector, these are handcrafted features, then we can learn pretty well by doing operations on these handcrafted features. So these are both of these types of approaches are very sort of I don't know how to say it. Like you as the algorithm designer have to apply this to your data, and then you feed it into some algorithm which does the rest. However, the neural network paradigm is somewhat different. So neural networks, those are kind of the focus of this next part of the class. And they're kind of the prevailing solution to machine learning problems nowadays. Neural networks, the sort of key thing that they do is they learn a representation. They learn a representation of the data from the data itself. Yeah, so it's kind of like the next step up. Instead of just learning how to convert from your data to some prediction, you actually learn how should we have to represent our data, and then once we've represented our data in this way, what do we do? So yeah, that's kind of that's sort of like the next level of models. And then once you've learned this representation, this learning of representations is kind of a very significant concept, and there's entire conferences. For example, there's the International Conference of Learning Representations, which is one of the premier conferences in machine learning right now. So this is kind of like the very hard and interesting part. But once you do that, then it's usually pretty simple. Then just a simple linear model or something will generally do pretty well. And the way I describe this is like you do one and then you do the other, but that's not really how it works. You kind of do both simultaneously for almost all applications, where somehow simultaneously you're finding the representation, and then given that representation, you're simultaneously figuring out how to optimize this linear model over it. But at the same time, then you're going to update your representation, and so on and so on. So, okay, that's the main idea behind neural networks, that we're going to learn a representation as well as how to use it. Okay, neural networks are often depicted pictorially. So let's do some drawings just to see what these will look like. So let's start with the simple perceptron, which you've already seen before, just to show you the type of way that we're going to be depicting some of these objects. So we're going to do it like this. We're going to focus on, say, d equals 2, just for simplicity. So x is the input as usual. And we're going to draw things like this. Let me draw it and then we'll explain it. So yeah, this is essentially, it might not look like it much, but it's a picture of a perceptron. In a sense, what this means is that the things that we have in the circles are going to be like variables of some sort. So here we have x, which is a 2D vector, just for simplicity. And these things on the edges generally represent parameters. So the sort of like the drawing with these nodes and these edges, this essentially means that what we're going to do is the thing on the right, the thing that will be, I mean, maybe these are kind of directed, and that could be, yeah, you can generally picture it as going left to right. So I'm not going to draw these arrows, but the idea is this node here, this variable here, that can be written as essentially the thing in the node to the left times this weight on it. So, and it's summed over all of these. So for example, this would be x1, I'll just write it x1, w1, where these are both scalars, and you just add them together or multiply them, plus x2, w2, plus b times 1, which I'll just write as b. And so you can write this as the inner product of x comma w plus b. And yeah, let me note that now I'm using this subscript to refer to dimensions of the vector. These aren't 0.1 and 0.2, this is just 1 point. Okay, so you can see here that this is the very familiar perceptron algorithm in terms of, or at least the perceptron model. Yeah, it'll just predict some value, which is an r, for the inner product of x and w, and then plus b. And you can also, if you want to make predictions which are 0, 1, you can just threshold this depending on whether it's greater or less than 0. Okay, so that's one thing. Let's make it let's maybe draw. I'll show you how this is related to another model you've also seen in this class, and that is logistic regression. I'm just going to draw another line here. You say y hat, and I'll write on this edge. Let me draw it like this maybe. This is going to be a bad picture, but like just draw it like this. And we have y hat, and I'll call this like sigmoid. So what I'm saying here is we're going to apply some function called the sigmoid function to this y tilde in order to get y hat. And this function is called the sigmoid. What is the sigmoid? Let me just write it, and we'll see why this is familiar. So the sigmoid is a function which takes in one input, and it's also sometimes represented as sigma of t, and it can be written as the following: 1 plus e to the minus t. So you can see that it's a function from R to R. It just takes a number and maps it to another number. And what happens if you plug this in here? Well, what you'll get is that y hat is equal to 1 over 1 plus exp minus inner product WB minus 1. Sorry, I wrote this wrong. WX minus B. And hopefully this should look familiar to you. Think for a sec about what this y hat represents. Well, you'll realize that this is just logistic regression. Yeah, if you think about it and you look back a bit, then you'll notice that this is exactly what a logistic regression model is and does. And so typically, yeah, what we can do is if this is your model, then given these parameters, you can plug in something and it'll give you this y hat. Now you can do many things with this y hat. You can threshold it, seeing if it's greater than 0.5, and if it's greater than 0.5, that implies that you should predict the label 1 for the point. Otherwise, you predict the label 0 or -1, depending on your standard. But yeah, it also represents the probability that if you sampled this, that you sampled this point, it's the probability that the label will be 1 given that the feature vector is x. Okay, so yeah, hopefully this is just review though. I'm not telling you anything new there. But the point is, this is logistic regression, and that's how you sort of represent it in a kind of drawing here. Okay, so that's nice and that's familiar. But now let's see how we essentially the point of neural networks will be that we take this and we just stack more layers next to each other. So let's try to. Before I get to that, actually, let me just comment a little bit more. No, I guess I just said that in words, so I don't think I need to write anything more. Okay, but so let's see what a very simple neural network will look like. Something which is just, instead of this one layer perceptron, yeah, I'm just going to sort of focus on this left part. I'm not going to much focus on the part after the sigmoid, but or including an after the sigmoid. But let's see what happens. This is just a one layer perceptron. Let's see what a 2-layer perceptron is, or a multi-layer perceptron, the sort of simplest possible multi-layer perceptron we can imagine is. So how should I draw this? Okay, let me draw it first of all, including what you already saw. And yeah, let's do this. So for reasons that may be mysterious for now, I'm going to call this H1 and H2, and this is going to be 1. And so we have here W1, W2, and B. So this is exactly what we had before. These names have been changed a little bit, but that's not too big a deal. But what we're going to do is we're going to actually, we don't have an input yet. Where this is just Perceptron by itself, but we're actually going to look at a slightly bigger model, which I'm going to draw as follows. Here. All right, this is going to get a bit messy here, I guess, but our best. 1, 1, U, 1, 2, U, 2, 1, U, 2, 2, and then here we have say C1, C2. And this is your first neural network. So like let's discuss what we have here. It might be a bit confusing or might not be clear, but essentially again, this part on the right here, this is the same perceptron that we had before. But what have we done now? What we do is we start with the input over here now. And what we do is first we have, we do sort of this linear combination, just similar to how we've done before. So let's write what each of these are in a bit more in sort of mathematical notation. So this here, let's say that this here is a different color, maybe a rectangle. So this here, right here, is this is called the input layer. And yeah, so that's the first thing, of course. And now what you see here is this z vector. This is going to be a linear combination of the input. So let's write it in vector notation. So z is equal to u times x plus c. So just sort of to spell some dimensions for you, z is a 2D vector, c is a 2D vector. You can see it's just two elements. X is going to be a 2D vector, and U here is a 2x2 matrix. And so that's all we do here. We just take the matrix product and then matrix vector product and add on this bias. What we do then is you can see I put this mysterious box, which I just put an F in. Well, I'm going to write this as H equals F of X. Now, I've been a bit mysterious here about what this means, but this is going to be what's known as an activation function. Which is going to map from R to R. So it's just a univariate function. You might notice that I applied it to a vector. Well, oh, sorry, let me be clear, not f of x, an f of z, obviously, because it takes in z. But you can see, even though it's a function from R to R, I applied it to this vector of length 2. But that just means we apply it point-wise, element-wise. So you apply f to z1, you apply f to z2, and you get a new vector h1, h2. This is a common notation. You'll see it a lot. A little bit of abusive notation maybe, but you should be comfortable with it. Cool. And then the final thing we do, well, you've already seen this. This part here is just y tilde is equal to the inner product of h and w plus b. And that's our entire thing. So yeah, let's just for a little bit more notation, or not notation, but just to explain some of the terminology used in these things. So this middle part here that is kind of new to this is what's known as a hidden layer. And why is this a hidden layer? Well, you can think of what the things you see are the input and the output. Let me draw the output layer here. Yeah, you can see, yeah, these are the ones you observe, of course, but these are things that kind of go on internal inside of the model, and you don't necessarily observe them, which is why they're called hidden. So those are the common terms. This is the activation function. It'll frequently be nonlinear. We'll talk a little bit more about activation functions in the future, but and I'll say nonlinear, and I'll explain a bit more what that means. It should be intuitive, though. It's nothing too fancy. It's just not a linear function. And yeah, we talked about learning representations. Well, this right here, this layer kind of second from the end, this layer here is going to be what is sometimes called the representation layer. And it's called the representation layer because, like I said, part of neural networks is about learning representations, and then you can apply simple transformations for it, which is why we call it that. This might seem a little bit trivial for you right now, just because it's only like it's 2, 3, 1 layer. I don't know, depends how you count the layers, but it's a small number of layers. But we'll see that for deeper networks, where perhaps the name deep learning comes from, this can be more, it could be more fancy, I guess, in the sense of what has happened up to this point. Okay, so this is essentially one of the simplest neural networks you can imagine. Okay, maybe the simplest neural network you can imagine is just logistic regression, literally, but yeah, this is one of the simplest, say, 2-layer neural networks. Okay, so now that we've got this stated, how good is this? For like, I said this is basically the simplest thing that's more complicated than a perceptron. Well, is this any good? Can it solve our problems with XOR? And I claim that it can. So let's revisit XOR, and we're going to refer to these equations here. So I'm going to, what are the parameters of this model? The parameters of this model, which are the things that we would have to learn from data, are this matrix U, this vector C, and this vector H, and vector W, and the B. So these 4 things here are the parameters that we're going to have to learn. So we typically, again, learn this from data we'll talk about training this, but let's just show that there exists some sort of neural network which can represent the XOR function. Remember, before we showed that no perceptron can represent XOR, so let's just see, like, can I show you a perceptron which can represent this? And I claim, yes, if we just choose the following parameters, which for now, I'm just going to magically present to you. Don't worry too much about where they come from. I'm just going to give you these parameters. Okay, and let's just try to see, oh, and also I have to specify this function, f, what is the activation function? This is not a parameter, it's you could think of it as a hyperparameter, something which, yeah, the algorithm designer has to specify and may affect the performance. But what we're going to use is a activation function, the most common activation function now, which is known as the ReLU, or ReLU, which is the following: max of 0, t. Very similar looking to the hinge loss, and like I said, this is called the ReLU, which stands for rectified linear unit. We'll talk about this a bit more later, but roughly what it looks like is it's going to be flat, and then it's going to be linear here. So this is 0, and this is the line t. So yeah, I just won't write that. So that's roughly what this function looks like. So okay, let's see what happens. Let's try out some of the points which were in XOR. So x1 is equal to 0, 0, and y1 is equal to -1. Well, let's just do some of these calculations. What is z? Z is going to be equal to ux plus c. Well, u times x, x1 here, this is just going to be the 0 vector, so that's ux is going to be 0, and plus c, this is going to give z is going to be equal to 0 minus 1. The next thing we do is apply the ReLU, so h is equal to f of z. Like I said, we just apply this point-wise, element-wise, so max of 0 and 0 is going to be 0, max of 0 and -1 is going to be 0. And then the final step is just we do this y tilde is equal to the inner product of h and w plus b. So this is going to be 0 vector, and therefore it gives you -1, which you'll note is exactly the y we were trying to predict. So it worked. It seemed like it worked in this case, and it might not be any surprise to you that the others will work as well. I'll do one more for you just to sort of maybe convince you and walk you through it. So what is z in this case? Well, z is going to be equal to ux. Sorry, I guess I should be clear, by the way. This is like really transpose of this because we treat it as a column vector. So yeah, ux, this is going to essentially just pick out a 1, 1 vector, and then we add it to 0, minus 1. So this gives you ux plus c is equal to 1, 0. Then applying the ReLU element-wise is going to be equal to 1, 0 because, yeah, there's no negatives. And then y tilde is equal to, well, what do we have here? It's going to be the inner product of h and w, which gives us a 2 minus 1 equals 1. And again, that's what we were trying to predict. So it seems like this worked for these two, and you can test it at the other two that it works as well. x3 is equal to 1, 0 transpose, and then y3 is equal to 1. And similarly, I'm not even going to write it all out. 1, 1. And then transpose, and it has equal to 1 for the y. So yeah, it seems like the power of this, that this somehow adding on this prefix to our perceptron made it more powerful, and now it can represent the XOR function. And kind of the power here is it somehow really came out of this ReLU. This non-linearity is really what made it work. In the sense that if I claim that if we didn't have this non-linearity here, then it would just be linear combination and a linear combination, and it would just be yet another. If you got rid of the non-linearity, that would just be a fancier ReLU in the end. So yeah, these kind of were key to it, and you need to have something that's non-linear there in order for this to work. So okay, this is just the simplest possible neural network. Let me show you a bit more generally. I'll try to draw a caricature of what things might look like. So I'll do this rather roughly, but so the input in general, we focused on the 1D case, or when it's a 2D thing, but in general it can be r to the d. So we'd have like x1 and x2, so on, all the way up to xd. So that's the input layer, as we discussed before. But then we would have some sort of hidden layer. Let me draw it like this. Here, this one would call maybe this layer would be called maybe z1, and we'd have some function f here, and then this would be h1. And let me copy paste this because otherwise it will be a lot of drawing. We have this, and maybe it's going to be, we'd have some number of neurons. Each of these is called a neuron. We'd have something like this. And just for drawing it, let's put it in a box, just because this is going to be our hidden layer. We'd have something like this. And then maybe we would have multiple hidden layers in our overall network. I'm just going to keep it relatively simple and just draw 2 to save some time. And then after this, we would have some output. So this would be maybe, we would call this Z2. This would be H2 for, these represent the entire vector that we have here. And then we would have some output here, which is, I don't know, it's going to be potentially a different dimension than before. So this is going to be y in r to the m, let's say, y tilde maybe. And of course, I didn't draw the edges yet, but we have to sort of connect this. And in the architectures that we're going to look at right now, you just connect them fully. So this is called a fully connected layer, or a fully connected neural network. That's another name for it. And you really just connect all of them up together in every layer like this. These are sometimes called dense layers as well, because you literally have every pair. Sometimes you might want sparse layers or some structure for these layers, but yeah, you can see that you really have to draw a lot of edges. Yeah, and so on, blah, blah, blah. Then for this, you similarly still connect it up. Yeah, I'll sketch it like this. So yeah, that's roughly what a more complex neural network might look like. Note that there's some dimensions which I will just comment on. The dimensions of these hidden layers, as we call them, they don't necessarily have to be bigger or smaller than the input and output. They could be either bigger or smaller. They could be the same. Whatever, we could have had 3 here, we could have had 100 here, we could have had more or less here. These are just different properties of neural networks, which may sometimes perform better or worse in various cases. And what we call sort of how wide it is here is of course, the width. So for example, if there were a lot of neurons here in a row, or I guess above, stacked on top of each other, like, yeah, if instead of 5 we had many of them, then that would be a very wide network. And how many layers we have sort of sequentially, this is, as you might guess, called the depth. So a very one with many layers would be a deep network. And yeah, the way you sort of compute this is exactly the same as we had before. So imagine, for example, there's some weight matrix here. So maybe W1, and this is going to be W2, and this is going to be W3. And we just compute things the way that we had before, for example, where you can define Z sup 1 is equal to W1 times X, and then we would have maybe H sup 1 is equal to this nonlinear activation function applied to the vector Z, and so on. Like from here, we would have that Z2 is equal to W sup 2 H1, and so on, just basically like that. Yeah, and that's a neural network. That's about all there is to it. You can stack many of these in a row. This is a fairly shallow one. It only has maybe 2 hidden layers. You can stack hundreds of them in a row, make them wider if you want, shallower. That's all there is to it. And as we had said before, this last thing right before the end, this will be, say, we'll call it sometimes the learned representation, or the representation layer. Okay, so now what will we have here? The next thing I want to comment on is, like, what do you do with so we have an input and we have some output. What do you do with this output? Because, before, when we were looking at, say, what are the perceptrons, sometimes when you just have this value here, this y tilde, that isn't very useful, in the sense that, okay, you can just say if it's greater than 0, then you predict 1. If it's less than 0, then you predict -1, and so on. But that wasn't maybe the most useful, and it was sometimes more useful to instead put the sigmoid on the end to transform it to something nice. And then if we define the right loss function, then this can be a more useful quantity if we do something like that. So yeah, this sort of sigmoid thing here is not very useful. So similarly, once you have this like last thing here, this y tilde, that might not necessarily be super useful. So let me elaborate on what we might do and what is common to do in many neural networks. Most neural networks is, suppose, so this is I'm going to take this learned representation here and just drag this over here. So ignore the rest of the network before this. So this is H, let's say. And then what we have is this y tilde, which is just a linear combination of the previous layer. And so on, blah, blah, blah. Yeah. But the key thing that we often do with this is apply what is known as the SoftMax operation. So yeah, this is an operation which essentially takes in a vector. I don't know how to draw this. I'm not sure if there's a normal way to draw this, but this is how I'm going to do it for now. But I'll just write it as this, SoftMax, and it'll give you some new vector, which we're going to call y hat. And what this SoftMax does is I guess it's a nonlinearity of some sorts, but it sort of serves a special purpose. It's a bit different, and it also does not it doesn't apply element-wise. So let's see what it actually is. So this vector y hat sub I is going to be a vector of length m. If this is length m, then this is going to be length m, and it's going to be defined as follows. It's going to be defined as y tilde of I, but normalized by this. Okay, so this is what is known as the SoftMax operation. Let me comment quite a few things about this. It's going to be, yeah, it's an important feature or function, and what does it do here? So there's many things it does. For example, you remember when we were talking about logistic regression? One of the issues with logistic regression is we had this parameterization, which was like, I don't know, y equals inner product of w comma x plus b. And the problem was that we were trying to interpret this as some probability. But the thing is, it was non-negative, or we need a probability to be between like 0 and 1. So this didn't really fit the bill when we did this. So we had to do some sort of transformation in order to make it something that's between 0 and 1. And that's the intuition behind what we're going to do here. This is a function which takes in, SoftMax is a function, which takes in an arbitrary vector and will convert it into a probability distribution. Yeah, that's right. This y hat is a probability distribution, and you can see that just by, if you sum it over I equals 1 through m, then the numerator will be the denominator, and it'll be it'll sum to 1. Furthermore, you can see that when you take exp of things, it maps arbitrary numbers to non-negative numbers, so it's going to be non-negative in each entry as well. Yeah, so therefore I claim that y hat sub I is a probability distribution. And how else should you interpret this? Let's also note the fact that you can think of this as so why did we even have their output being m dimensions? Well, this is useful in the case where we have an m class problem. Say there's m different things that the input could be, or m different labels we want to apply, and you just basically have a parameter or a node to represent each of those different classes it could be. So then when you apply the softmax, it'll essentially tell you, it's essentially like the neural network is telling you, this is my probability distribution over what I think that the neural network, over what I think the input's label should be. So for example, if it's possible and perhaps common that one of these entries will be very, very large, like 99.9%, and then everything else will be tiny, in which case it says, it's kind of like saying that I'm 99.9% sure that the label should be the whatever came out that whatever had that much value. So that is the idea behind SoftMax. It's essentially going to convert it to some probabilities of predictions. Yeah, if you want to do a prediction with, oh yeah, one more thing I want to mention here is that note that when you take an exp of a number, it'll become very large. So it's kind of going to try to make the biggest element sort of even bigger. So just to, I don't know, maybe you can see this for yourself, but if you have an element where everything is like 1, and then you have one thing where it's like 5, then say e to the 5 is going to be much bigger than e to the 1. So it kind of amplifies the differences between them. The biggest one, if one is bigger than all the others, then it'll be much, much bigger after you apply this operation, which is kind of why it's called softmax. Sometimes ideally you would like to just be able to pick out things which just puts a 1 where, yeah, ideally if you just want a hard prediction, what you could just do is that you would put a 1 in the coordinate which is maximum and everything else would be a 0. But that's not very convenient for optimization algorithm because we're going to need to take a gradient. And while the max function is not differentiable, softmax actually is, which is pretty much why we use it. Among other interpretations like these probabilities and confidences. So yeah, just as one more note, I'll mention that this is basically before when we just had one possibility, which when we were doing logistic regression, then we had this function, which is the sigmoid function. And you can think of softmax as just a kind of generalization of the sigmoid function. This is just sort of the m equals 2 case, though since they're kind of redundant, we just do use it only with 1. But yeah, if you just think of the natural way to generalize sigmoid to having more than one input, then SoftMax is the right answer. And so this will factor into our loss. So what is our loss function? Whenever typically when we're training neural networks, we're going to use what's known as the cross entropy loss. And you've actually seen this already when we talked about logistic regression, in the sense that the loss function, so recall that a loss function, it takes in a true label as well as a predicted label. Or maybe the way you can see it is, I guess the way we've described it is, let me write it like this, because this is how we've talked about it before. It takes in a point, x and y, and it has some parameter vector, theta, which I'll use theta to represent all the parameters of the model. And so the typical loss function that we use is the following, which is known as, again, the cross entropy loss. And it's summing over all possible classifications of yi log yi hat, where recall that yi hat is equal to some complicated function, basically applying this, like let's call it some g, which depends on theta of the x. Let me say it like, I guess I wrote it as a, let me write it like this, where y hat is basically, you take the input, you run it through this neural network, and that gives you some prediction vector, and then you just take this cross entropy loss. So now let's just recall basically let's make sure we understand what all of these things represent. This y hat, again, is going to be the prediction vector out of the neural network. And this yi, you might be wondering, like, aren't we just feeding in one label? Well, you're correct. This is sort of a cheap trick here in terms of notation. What we really did here was you can think of this yi here as being a one-hot encoding. That is, yi here will be 1 if this label y, if the label y is equal to I, and 0 elsewhere. So let me just write this here as like one hot encoding of y. Yeah, you can think of this vector that we're using here as going to be just 1, where this is a 1, and it's going to be a 1 corresponding to the index which corresponds to this label, and 0 everywhere else. So yeah, that is the common loss function, which is a generalization of the loss function that we use for logistic regression. Cool. Okay, that's that. The next thing I want to tell you about is activation functions. We kind of talked a little bit about these functions f, but let's discuss a little bit more about them. So activation functions. And what are the sort of common ones? Well, let me tell you, first of all, I've already think I emphasized this, but we generally want nonlinear functions. What do I mean by nonlinear? That is, we want a function which doesn't just rescale and maybe add a number onto a thing. And I've already shown you, in fact, two of the best known nonlinearities. So one is called sigmoid, which you've already seen, and we'll just recall that this is sigma t is equal to 1 over 1 plus e to the minus t, which is also equal, if you write it a different way, e to the t over 1 plus e to the t. So yeah, while this is used as the last layer in a logistic regression, it's also an activation function, which we sometimes use in the middle. And let me draw a picture for what this looks like. Well, this is going to be terrible. I apologize in advance, but let's see. It looks something like this. Yeah, picture that's a straight line. So yeah, this goes from 0 to 1. Yeah. So what do I want to say? sorry, does this go from 0 to 1? Let's check this real quick. Maybe it goes from 1/2. I always get the scaling wrong. So if we put in minus infinity here, then it'll be e to the infinity, and this would dominate, so this would be 0 indeed. And if we put in infinity here, then this would be e to the minus infinity, so this would be 0 here, and it goes to 1. Yeah, so that's correct. The next common one that's sometimes used, not so much anymore, but it's called tanh, which is the hyperbolic tangent, which maybe you remember from a math class, but it's also useful here, and it's written like this. And it looks very similar to this one. We'll draw it in a separate axes, actually. Maybe one difference is that it can, I think, be negative. Yeah, it can be negative, and it looks something more like, it looks kind of like the same thing shifted down, though it looks like a little bit different at some points, but yeah, something like this. Yeah, so these are two of the sort of classic activation functions. And I guess one of the key things, like I said, is that they're nonlinear, which is useful. But the thing is that is not great about these is that they have what's known as a saturating property, in the sense that if you take a look when you go off for the input being like very small or very large, well, you'll notice that this kind of flattens out. It should be a flat line pretty much when you go far enough out. It would have a very, very small derivative. And this is actually a problem, because remember, when we're doing this peeking ahead a bit, but when we do gradient descent, we need to compute a derivative. And if your derivative at some point is 0, this essentially kills all signal you had in your derivative. So because of the fact that these go very, very flat, that essentially means that your derivative will die and you won't be able to take a good step using gradient descent. So that is a bad thing. Instead, what is more popular nowadays is the ReLU activation, which I already mentioned to you, the rectified linear unit. And again, this is ReLU of t, which is equal to max of 0 and t. And maybe I don't have to draw this again, but I will anyway. It can be drawn like, very quickly. It's easier to draw than these other two, but it looks something like this. It's going to be 0, and then it's going to be linear afterwards. And this solves the problem, at least on one end, where the fact that if you have large numbers, then the things saturate, because here the derivative, you can see here it'll be 0 if it's to the left of 0, and it'll be 1 if it's to the right. So it's going to be it's kind of, you can think of it as like a gate, where if it's negative, then it doesn't allow the gradient through, but if it's on the right, then it's going to be a 1, and it'll just multiply the gradient through easily with just a 1. Yeah, you might think it has the same problem when you go negative, which is kind of true, but it doesn't really seem to cause much of a problem. And you can also replace it with what's known as a leaky ReLU, which is just kind of a slight negative line over there. So yeah, these are the most popular, some of the most popular activation functions. There's really a ton. People will invent new ones just to try to say it's better than others. But yeah, ReLU is kind of the tried and true, generally the best one that in most cases. Okay, so now I've told you everything about how to sort of define a neural network and what we need to go into, at least the basic multi-layer perceptrons. Let's talk about how to train one. Yeah, how to train your neural network. And this is going to be done essentially the same way we've trained absolutely everything else in this course so far. Pretty much modulo 1 or 2 things. But yeah, what does training even mean? Well, training means that, again, there's some unknown parameters and we have to determine them. So for this picture as I drew it here, we'd have to determine the W1 matrix, we'd have to determine the W2 matrix, we'd have to determine the W3 matrix. Essentially all these like coefficients and all of these things here. Before we just had one, maybe this W3 was the only thing before, but now we have a bunch more parameters. And so we have to determine the weights. And maybe biases if we have them. I just didn't draw them in that picture. And so the way we do this, despite the fact that they look a little bit more complicated, it really isn't that bad in the sense that we just do it the same way we've done before. All we do is we define a loss function, and then we try to minimize it. So let's say we're trying to argmin over theta some loss L, which is going to be equal to just what we've done before, 1 over n summation from I equals 1 to n of the loss of yi, comma, y. I guess I wrote it as in the previous thing as xi, yi, so I'll just do that again. And with respect to theta here. So yeah, this is all we do. We just define some loss function where I guess we already talked about what we commonly use, this cross entropy loss. I will comment that it might seem like a very simple loss function, and it kind of is, but this actually encodes a lot in the sense that, just to recall what I said before, this y hat here, the sort of like predictions, this is a very complicated function in the sense that it's essentially computing this function. So this little y hat here really encodes everything that happened in the way here. So that's what's going on. And correspondingly, that makes it a little bit more complicated than before, where when we're going to try to run gradient descent. So, oh yeah, sorry, let me also mention that these are the parameters. Like, while it's not so simple as it was before, where we just have one parameter vector, maybe w, this time we're just still going to try to find the set of all w's, which we plug in as those three matrices, or however many matrices there are, and those will be our parameter vectors. That'll be our parameter vector, which can be large. But again, all we have to do is run gradient descent. Recall what gradient descent does. It will take the gradient of this loss function, and it will then take steps in the parameter vector in order to optimize it. So like, just to sketch it out here, I'm not gonna be too formal, but like basically theta t is equal to theta of t minus 1 minus eta with some learning rate, eta sub t maybe, times the gradient of L at whatever point theta sub t minus 1. So yeah, something roughly like that is our gradient update, just to refresh you. And this should look pretty familiar. The only thing which may be not obvious here is how to take this gradient. This gradient is kind of the questionable thing here, in the sense that yeah, before you could just see by hand, okay, here is what the function looks like. Well, we can just compute the gradient kind of just by doing it by hand, and yeah, it's not too bad. But here, remember that our function is going to be something much crazier here. Our loss function depends on all of this stuff going on in the middle here. So maybe this is not something you want to do by hand. So fortunately, the good news is that computers are very, very good at taking derivatives, and they can essentially do this for you. There are tools which are known as automatic differentiation, or sometimes referred to as autodiff. This might actually refer to a specific implementation, I'm not sure. But yeah, just to save myself some writing, automatic differentiation. And there is a key algorithm, which was kind of one of the most important ones in machine learning, or in deep learning in general. And that is known as the backpropagation algorithm. So backpropagation, it's sometimes a misused phrase, but what it means in particular is the algorithm which is used to compute this gradient. So you use backpropagation to find the gradient, and then you take gradient steps. That's all backpropagation is, sometimes called just backprop. And this might seem intimidating, but really, like, if you just think back to your calculus classes, well, it looks like a complicated function, but it's really just using the chain rule, maybe with a bit of dynamic programming in order to make it more efficient. that's all backpropagation is. And so I'm not going to go into the full details of like backpropagation. I'm going to just try to give you an idea. I'm not going to do all the calculations because I think there's much better resources than what I could tell you in sort of just a few short minutes. So I'm going to link in the description what I think is an awesome coverage of how to do backpropagation. And not how to do backpropagation, but what it's really doing underneath the hood and why it works. But in the time we have, I'm going to at least just quickly try to explain and give you some intuition as to why it's why I say it's the chain rule plus dynamic programming. So let's just do a very simple case. The idea of, in general, like what do we want? Like recall what we want. We want the gradient with respect to theta of L. That's kind of what we're trying to compute here. And yeah, so we're trying to basically find a gradient with something with respect to a different thing. And the thing is, what we're trying to find, I'm just coming back to this picture to say that we're trying to find the gradient with respect to things which may be earlier in the network or later in the network and so on. Like there might be a big difference. We have to find, say, the gradient of the loss function with respect to these parameters all the way at the beginning. And so it's not necessarily how clear how to do that, but it's not too bad if you just remember the chain rule. So let's start with a simple case. Suppose we had x, which is in R, and we have f and g, which are both univariate functions. So I'm just going to start off very simple. And let's just say that y is equal to g of x. And then we also have that z is equal to f of y, or that is f of g of x equivalently. So this is just a very simple function, and let's suppose we wanted to compute dz of dx. This is basically what we want here, like gradient of L with respect to theta. It uses a lot more fancier symbols, but really it's just taking the gradient, the partials with respect to every element of this parameter vector. Well, we can just stick with one-dimensional derivatives, and it kind of shows the idea. And how do you take this derivative? Well, you can break it up into different component derivatives. So you can just write it as dz dy times dy dx, which is a lot easier to do in the sense that you can compute each of these sort of stages in the differentiation without too much trouble. You can take, like, just focus on this, and you can take the derivative without too much trouble. And similarly, you can take the derivative here without too much trouble. So if you can do those independently by their own, then you can just multiply them and put them together. And this is the chain rule. And that's kind of, at its core, all that backpropagation is. So let me maybe draw a picture to try to hammer this home a little bit more, just try to illustrate. And I'll just draw a very, very simple and kind of dumb neural network. X, U, Z, put it through nonlinearity, F, and then out here comes another thing, H, W, Y. So, okay, suppose what we want is recall, we're going to want the derivative of some loss function. I guess, yeah, let's sort of put it through and we get L, because, yeah, that's what we want. Well, we can just, what we want is basically dl with respect to w, and we want dl with respect to u, because those are our two parameters in this very simple neural network. And what we can do is we can just work backwards, in the sense that that's why they call it backpropagation. So, okay, let me tell you two things. There's what's known as a forward pass through the network, and that's when you put in an input, like you say you put an x here, you put an x, and then it'll compute z by applying u, and then it'll go through here, and basically you take the forward pass through the network. And then what the idea is, backpropagation is going to work in the opposite direction. It's going to take derivatives starting from the end and is going to work its way back to the beginning. And the calculations that it would do in this case is something like the following. We would calculate first, like, the derivative of L with respect to y, because that's kind of the first thing here. Then we would compute dy times d by dw. You compute d sorry, what else? Yeah, we would compute dh, sorry, dy by dh, dh by dz, and dz by du. So these are the various things we'd calculate. Why do we calculate each of them, and why don't we calculate a few things? Like, you might be thinking, why did I skip some of these? Okay, the reason why is that what do we really want at the end? Like I said, what we want is dl by dw, and this can be written as dl by dy times dy by dw. And you can see that we computed both of these right here and here. And similarly, the change in the loss function with respect to the other parameter, dl by du, well, this is a few more multiplications, but it's a dl by dy times dy by dw times, sorry, not that, it's dy by dh times dh by dz times dz by du. So yeah, there's a few more multiplications here, but you can see we got there in the end. Let me note that we didn't, which ones didn't we calculate? We didn't calculate dz by dx because we don't really care about how things depend on the input x. That's not really too important for our applications of computing the partials with respect to w and u. Yeah, in fact, we kind of just did the bare minimum in order to be able to find out the derivative with respect to w and u. The only reason we calculated something like dh dz is not because we care about this derivative in of itself, but because we needed it to be able to calculate the derivative with respect to u. So yeah, that's the basic idea behind backpropagation. Of course, this is a very simple example. Let me just give you one more, I'll make one more point, or try to make one more point. Let's revisit, and then maybe it'll give you some idea of how these calculations will actually go, because of course this is silly. Nobody does like one variable neural networks. This is a bit simplistic, but we're just going to kind of revisit this case where instead I'm going to make x, y, and z vectors rather than just single elements. So let's say we have x in Rm, something like this, and then we have g, which is a function from Rm to Rn, and then we have f, which is a function from Rn to R. And then, yeah, sorry, a lot of notation, but we do similarly as we did before, equals f of y, which is equal to f of g of x. Basically the same sort of sequential operation. Now, here in this case, if you apply the chain rule again, I'm not going to do the derivation, but hopefully you can verify this for yourself. But the partial, what we care about, suppose, is the partial of z with respect to, say, some single element xi. And this can be written as summation over all j, partial z, partial yj, times partial yj by partial with respect to xi. So yeah, it's basically a very similar thing to what we did before, but because now there's kind of many paths from z to xi, we kind of have to take all of these paths from one to the other and sum up over all of them. That's just the chain rule. Yeah, so that's like the sort of basic calculus way of doing it. But you can also, if you write this using matrix vector notation, then this can be rewritten as the following, which is more convenient and might be clearer as to what we're actually doing, or maybe not, I guess. But let me write this and then we can discuss it. Yeah, the notation here is going to be a bit weird, so I'll try to explain what we're doing. So this here is actually a Jacobian matrix. And recall that a Jacobian matrix is going to be basically the partials of all yi with respect to partials of all zj, And so if you do it out, this should be an n by m matrix. Okay, and what does this say? This says that if we want the gradient with respect to x, then what we can do is we can take the gradient with respect to y, which is the intermediate thing, and then do a matrix vector product with the Jacobian of the other layer. So yeah, that's it kind of just decomposes it into two layers. So just to maybe go back to one of these pictures, which I have so many times, essentially it's saying that if you want to find the partial of maybe, I don't know, this layer with respect to this layer, well, it gives you a very nice way of decomposing that, in the sense that it says find the partial of this layer, or the gradient of this layer with respect to this layer, and then, which you can do kind of recursively, after you find that gradient, then you can just multiply it somehow by the Jacobian of the kind of conversion in between. And for this type of layer, it's very simple. It's a little bit more complicated for something like this when you have to take the Jacobian, but it's just actually the parameter vector. But yeah, so I'm getting a bit lost in details here. The main idea that gives you a way of decomposing a gradient into sort of the two layers that comprise it. And all backpropagation does is really does this type of decomposition and really computes things in the right order to not use too much memory. Yeah, that's kind of one of the most important things, the fact that backpropagation has been highly optimized in modern programming languages and modern libraries to be able to do this in a very memory efficient way, which is doable on very large neural networks. So while I've described it here for like very silly little networks, and even I claim that this is a tiny network compared to some of the crazy things that you might see, where you have billions or even trillions of edges, let's say, and you can still backpropagate through some crazy things like that. So yeah, while I sort of simplify it a bit here and look at some simplistic cases, this is a very powerful algorithm, which is really pretty simple in, yeah, it's comparatively simple given how powerful it seems to be. So yeah, that's backpropagation. Again, that's all I'm going to go into it. I recommend checking out the videos I'm going to link in the description. The final thing I'm going to mention today is some very basic theory about this, about neural networks, in the sense that they're universal in some sense. What does it mean that they are universal? It means essentially that they can, if you have any function, then a neural network can represent it. And a very simple neural network. Let's be a little bit more precise. Suppose you have any continuous function g, so this, say, let's take in some input from 0, 1 to d to r. So yeah, that's basically just something which takes in the x's are d-dimensional and the y's are just a single number. So any continuous function can be approximated arbitrarily well by some two-layer neural network with an arbitrary nonlinear, or sorry, arbitrary non-polynomial activation. So that's, I think, pretty powerful in some sense. It says that any function, any continuous function you can possibly think of, you just need a very simple function, a very simple neural network to represent it. It'll be something like this, where this is the input layer and the output layer is going to be here. And then you're going to have some intermediate layer here, which is like the hidden layer, I guess. Let me draw it a little bit wider just because we had this big little setup here. So hidden, and then we have some like nonlinear activations in the middle. It has to, in this case, be non-polynomial actually. for this theorem to hold, though if you have a slightly deeper network, then you can actually get rid of this non-polynomial. It just has to be nonlinear. But yeah, if you just have some simple little network like this, then this is able to approximate any continuous function as long as you put the right weights on these things. That's quite powerful, and it leads to the statement that neural networks can be universal approximators, I guess is the term that's sometimes used. So yeah, this might sound cool. I'll note that this is also true for kernels. Like kernels can let you represent basically anything as well. So maybe that's not where all the power from neural networks comes from. Yeah, because they seem to be more powerful than kernels in particular. Another drawback of this type of theorem is that when I say just a simple network like this, the thing I'm sweeping under the rug or hiding is the fact that this middle layer, this hidden layer, may be very, very wide. It might require us to have like an enormous number of nodes here in terms of the width in order to be able to do the approximation. So it could be exponentially large. So that's something that is not too pleasant in terms of approximating. So on the other hand, if you make it a bit deeper, then these theoretical results, you can say then you don't need as much width in order if you instead have a bit more depth. So yeah, this is just kind of an interesting fact. It's not necessarily why neural networks are so powerful. It's a good thing to know that they're not going to fail at representing things just because if you make it big enough, then it'll be fine. But yeah, it's a good fact to know. So yeah, that's all there is for today. We talked about what the definition of a multi-layer perceptron is, which is kind of the simplest possible type of neural network, or kind of the first deep network in some sense. And we talked about a bunch of the different terminology, as well as backpropagation and some theory about it. So good. Yeah, next time I think we're going to talk a little bit more about important topics within neural networks as well.